Hey Jeff, if you can hear me, I can't hear anything.
How about now?
Yes, thank you.
Oh. Hi, Tanya.
Hi,
Sorry about
morning.
that. Okay, we're revisiting the idea of streams in, out, and error. For echo, hello. When I hit enter, all of those streams start running simultaneous processes. And what were they in this example? Standard in. Um, hello, where did that come from? Smashing keyboard. That's the standard in by default. Things are looking for smash keyboard. A few programs, as we'll see here in a second, are actually looking for a file as their standard in. So they want to read the contents of the file, not read the keyboard smash. Standard out. The keyboard. Whatever you click, just move it again. Where'd it go? Screen. Okay. That is almost always, even more so, almost always the general location for your standard out. It goes to screen. And then standard error usually goes to screen also. In this case, it went to the screen and it was empty. Okay. Those three streams are always happening. We can have more. So that's with 0, 1, and 2. We can start naming new streams and we can have 3, 4, 5, whatever. There may be a time when we need to worry about that, but just know that it's possible.
What would the other streams be?
Sometimes when you're interacting with another computer, it doesn't want to read from your error stream, but some programs put, this is stupid, they put useful information in the error stream that's not error messages. Because they just treat it like, here's another stream. Like, it's easier just to send it to that existing stream. And so that starts complicating things. And so you need to type your error into stream number 3 or 4 or 5. And then the other computer.
So you'd be like splitting one of these like three into like some.
You take the error stream and instead of sending it to stream number 2, which is the normal error stream, you split it with a little t. And you go send it to number 3 also. And that's the only one the computer can read because it's been told not to read your error stream, which makes good sense on that part. Bad sense from a programmer's point of view. You shouldn't be putting useful info in your error stream, but people do. Why? Bioinformatics software is not written by professional software developers. It's written by grad students who just needed to get something done. And so it tends to follow this principle. It's just a house of cards. So this class is the duct tape, wires, and WD-40 of how to work with other people's bad software. So just know that that's possible. Those streams are not magic, but those 0, 1, 2 are always designated and always running. So yeah, we had our standard in coming from the keyboard. It went to a program. The program was echo. There was our standard input, and its entire thing is to take standard input and send it to standard output. That's the entire purpose of the program echo. Not super useful if it's just going back to your display because you just type something. But getting a bit more useful because it can echo the value of variables in your environment. It will interpret those values and send it to your screen or send that to another file. How do we get it to go to a file instead? Greater than, yes. So I'll hit up to go back up here. Echo home. Redirect to a file that I'll just call my home. And there it went. The standard output got redirected away from the screen into a file. So now if I look around, I see it right there, this brand new file that it created. I can hack the contents of that file and see what's in there. Okay, so that's a redirect. Doing the single greater than is different than doing double. What's the difference? This is appending, and so if I send with the 2 to my home, send that standard out, I should have 2 lines in there. At my home. Oops. What just happened? I accidentally hit backslash there right before enter, and so my prompt is saying, still waiting for instructions. Control C, my way up. Fill up your cap on home. And there they are. Okay. I hate this file, so I'm going to remove my home. And now I'm going to collect your assignments. I wrote a script to do that. Up to date, cool. Nobody's pushed any last minute changes. I did this like 20 minutes ago. Not everyone's homework. Okay. Here's that little script that I wrote. That's it. It's just 3 little lines. And today we're going to see what they all mean. But quickly walk you through it. Don't take notes on this. This is saying this is a bash script. At the top of some scripts that you'll see is that. That means, hey, hey computer, you're about to see code written in Python. Do you know how to interpret that? And this is saying where the interpreter is, so where that language is stored in the computer. For us, it's in our root bin bash. The language bash is stored there, and it's interpreting these lines of code as bash code instead of Python or Ruby or Go or anything else. And then I'm just looking through all the files and folders that I see where I am that have an underscore. So that's all of your names. And then I'm going to echo the current value of those, go into them, into biocomputing, do a git pull, and then go back to it. So it's just automating all the git pulls. So we've got our streams, we've got redirect to file, and then this is what we didn't really have time to get into last time, was the pipe, as in pipeline, bioinformatics pipeline. This redirects standard output also, but it doesn't send it to a file, it sends it where? Another program. Okay. So the pipe's job in the bash language is it takes standard output from one program and it turns it into standard input for the next program. So we can start chaining these programs together. All right, in this right here, echo hi mom pipe WC/C, that's word count the characters. For the byte filling. What are the programs? We got 2, echo and WC. Standard output from program 1, where did it go? To the standard input for WC. Okay, so the standard in for program number 2 was the standard out from here. So we can chain them together. So if I say LL type WC dash L, that's word count, but just give me the lines. I get the number 17. If I just say LL, here's the standard output. Put this down a bit. 1, 2, 3, 4, 5, 6, 17. Okay, so that's standard output that went to my screen. Instead, I'm saying, no, send that to the word count program. Tell me how many lines you were going to print to the screen, basically. That's 17. So we've seen a few Unix programs. Cat, contents of standard input, sparse them up. Okay. Typically it looks for files, but you can send standard output from any program in cat. So CAC. This is clever, just does it backwards. So starting from the last line and then up. So let's try that one. LL TAC. It's in reverse order. Head. Give the first n lines of the standard input. LL type head, and this is how head wants it, is tell it how many lines to give. So dash n3 gives me the first 3 lines of that standard input. Sends those to standard output. I'll hit the up. What's going to happen here?
It's the state first.
Save what to a file?
Save the output of actually, so that's very nice.
Yeah, so that stuff that just went on my screen, those first 3 lines, will now be redirected to a file. And so we can chain together types and redirect the file all we want. This is actually a really handy process here. And this is a very simple case, but we can go into a file that's 20 gigabytes and find just the lines that match a certain pattern and send those to a new file. We can do that with just a couple programs and a redirect. That's really handy if you're looking for a certain pattern in DNA, for example, and you have this huge set of files. You can search through them all, find all the ones that have this pattern you're looking for, and send the names of those sequences to another file, and boom, you get yourself an answer. And the way that Bash works, it's a lot faster than Python or R or Go. The only thing faster than Bash is like Rust, maybe C++, because it works line by line, because it's got streams. And so these streams let it process any size file. It doesn't have to memorize 20 terabytes. It looks at everything top to bottom, one line at a time. And so memory requirements aren't an issue. It's just going to read through and chug through the biggest files you can give it one line at a time and send them out. So that's head. What do you think tail does? The last n lines of standard input. So I can say head 3 here, right? I'll change that to head 5. And then I can pipe that to tail and 1. And what am I going to get? Listing everything long ways, taking the first 5 things, and then taking the last one of those. I should see Dan already. So if we combine head and tail, we can get any placement we want. Right? You want line 104 and say, give me the first 104 lines and give me the last. There is no give me line number 104 command, because people who wrote this program were like, that would be dumb. All you need to do is chain these 2 together. And that's the Unix philosophy. It's really simple, kind of dumb in their own right programs that can be chained together in handy ways. All right, cut. We don't have anything for a good example here. Yeah, we do. So this splits your standard input on some character into columns. So LL, type that to cut. And cut wants two things. It wants a dash D and a dash F. So that dash D is saying, what's your delimiter? How are you going to split this up? And it wants a single character. Yeah.
Oh, is that one like for Excel, like comma eliminated?
Mhm. So we can take a comma separated values file, a CSV, and use cut to split it on commas, and then say, give me the third thing. So we can take a file that's any size with 20 million columns that won't even fit into Excel. Can't open that file in Excel, but here you can just say, yeah, cut it on a comma, or I'm going to cut on a space because I don't have any commas in my files here. So cut on a space. And then it wants the field, and it wants this by number. So I could say field 1, and it's giving me the first thing on the left of the first delimiter right there. I want 1 and 4. So it takes a little comma separated list. 1 and 5. 1 and 6. 1 and 10.
Is the one going to take the column number?
Column numbers. Yep. And the column numbers of this if you split it up just on space. So we can say LL pipe head and give me the first 5, and then cut those first 5 up on a delimiter of a space, and then give me field 5. I mean, that's a lot of nonsense looking stuff there, but it did exactly what we asked it. The cut can be part of our little toolkit that we start throwing into our pipelines. This is very handy with a lot of genomic data that's comma or tab separated.
So if you have like file, there's like multiple spaces. Are they doing one or does it get rid of every space?
Every time it sees a space, it'll split into a new column.
Okay, so if you have like multiple spaces, it'd be like 2 empty columns, like 4 empty columns.
Which is why you don't want to use spaces to delineate columns. You want to use tab or comma. Paste. This is the opposite of cut. You can paste together columns. TR is pretty handy. It translates one character to another. So if I list everything and pipe that to translate, it wants 2 things in quotes. And it's basically going to say, like, translate a space into an underscore. There you have it. Here's a special character, the first one that you're seeing. \n is actually a single character. It means new line. So I'm going to translate every new line, which is just the enter button, into underscore. So it stuck it all on one line and put an underscore between where each new line would have been. That's a handy special character to know. \s is any white space, so tab or space.
Is this the individual space or so?
Individual white space. \t is a tab. See any of those? Okay. That's TR to translate. And then we've got sort. Hello. Type that to sort. How did it sort this?
And sort of the first number itself, or
Alphabetically by default. So it's looking at D, R, W, X, R, W, X, R. Yeah, and then the numbers, one being, yeah, so it's sorting it, but we can tell it how to sort stuff. We can give sort a -n, for example, say, hey, you're going to be seeing numbers. It's not going to like it in this case because it's actually saying letters. But okay. You can give it a K, say sort on this field, sort on field 3. We'll try to split it up. So sorting does that. Unique removes any 2 lines that are next to each other. It turns them into 1 line, so it just gives you a unique value. So let's try this. Echo A. See if this works. New line B, C. No, it doesn't like that. What if I put this in single quotes? No, hates it. Okay, let's do this. Touch A through A through C. One, 2, 4. Oh, crap. There we go. I hate this. Move 1 star, 2 star, 3 star. Touch. File. Underscore. A, C.
It's like the star things like sensitive.
I haven't taught you about that, but it's not, it is sensitive to case,
Okay.
and it's just a wild card. We'll start using it very soon. This was a bad example, Jeff, because I can't have 2 files named the same thing in the same directory. Move anything that starts with file and then ends with whatever. So I'm going to create a new file. Okay. Save that. Cat, new file. Okay. Now we can see sort in action. Type cat new file and then send instead of to my screen to sort, and it puts them in order. And then I can type that to unique. But unique only works if things are sorted first. Cat new file, type to unique. It'll only get rid of things that are next to each other in the same. Yeah.
Why does it have to be sorted? Like it's not say going with the unique values, it has to be in the certain.
Okay, good question.
Yeah.
Why indeed? The way that streams work, since we're doing 1 line at a time, it's a million times more efficient for it to actually have it pre-sorted than to have to suddenly memorize your entire file and then see how many times it's done. This makes it efficient for huge files. Yeah.
for the sort, like -3, argument, is that also columns?
Mhm.
Like,
Yes.
Yeah, what is the HQ?
It lets you sort on a certain column. Let's go ahead and do it. So I'm gonna open up new file, and I'll hit tab B here, tab C, tab D, B. Okay, so we've got a tab. That's the default for a new column for sorting and cutting and everything. Save this. So cat new file, there it is. Sort K2 says like, I want you to sort on column 2 instead of column 1. There it is.
So it starts on 1, it doesn't start on 0 or anything?
Starts on 1. It's the same language. I love starting on 1 instead of 0. Yeah. It's always bothered me about Python.
Oh, I just.
Yeah, so we say that this is one indexed bash language. One index. It starts counting on 1 like a normal person.
Could you do it by rows as well? With
That's
the
a
sort?
different program.
Oh,
Yeah. And that one's a bit more complicated, so we'll save it for now. But you will be using it a lot. It's said the streaming editor. Unfortunately, it has its own language associated. Same with grep, but we're going to start with grep. Global regular expression pattern. This is just a pattern matching sort of thing. So I'm going to sort by K2 and then pipe that to grep. Now, when you start getting really nerdy about command line stuff, you're going to meet people who use grep in colloquial speech and to look for something. Let me grab that for you. I have been known to. I try not to, especially in the general population, get you some weird looks. But grep has been around since Bash was created. And in fact, the first programming language of all time was basically just grep, which was you have a pattern, you match it, and you can change it. And so let's just give it a pattern. The easiest way to use grep is say like, hey, look for the pattern lowercase a. It found them. Finds things really quick. It's a very, very like speedy algorithm, the way it works. Yeah.
Why are they red?
Because I have color equals auto set up here on my computer. That highlights the patterns that match. Yeah.
I just want to put a line
Line by line. I can look for lowercase b. And it's line by line. If it finds it in a line, it gives you the whole line. That's grep's job. So the way it works is it's streaming through whatever standard input you gave it, in this case, the sorted contents of new file. And when it sees that pattern, it sends it down the pipeline to standard output. If it doesn't see that pattern, it doesn't. grep has a whole bunch, grep dash help of stuff that you can do. Look at all this.
Does grep also need to be sorted before you can use it?
No.
Okay,
Thankfully, no.
is there a reason why we sorted it in this case?
Just because I hit the up key and
Okay.
that was the sorted stuff. All right, so we can grep using Perl regular expressions, which is a different flavor of pattern matching. Basic ones, extended regular expressions. We can grep for fixed strings, so if it finds exactly this with no other context around the string, We can grep from a file, so we can have a file of patterns that we're looking for. So think a bunch of gene names in a file. Here's the genes I'm looking for in this file. Boom, you can grep from that against 20 gigs, no problem. A dash I means ignore case, so it won't matter if it's capitalized or lowercase. Also very handy for genomic data where it's sometimes lowercase, sometimes upper. Okay, we can grep for entire only whole words or entire only whole lines. So like a whole word would be, does it have this pattern exactly, and then spaces around it. Lowercase v, this one's pretty handy. Invert your match. Give me the non-matching lines. So there's a whole bunch of these. Capital B is give me the stuff that you found and this many lines before you found it. Yeah.
The dash H doesn't work for this nice stuff.
Dash H works sometimes. I always try it first and then it says, hey, use this. Oh, okay.
For some reason, like when I do graph dash help, I just get like a list of like constant inputs rather than like the full like help recipe.
Try this. Man grep. That's the manual for grep.
Okay.
That works.
Yeah.
And that's, you can scroll up and down with your arrow keys. And that's the full explanation of everything. This is easier done by just Googling grep manual. And it gives you the exact same output here. If you want to get out of this, Q to quit. Okay, so wherever, all right, we can grep for B. If I wanted to find all the lines that didn't have a B in them, I need the inverse. All right, this is a little pipeline. Cat new file and sort it, and then grep for the inverse of pattern B, and then WC-L. What question is this little pipeline going to answer?
How many rows don't have E?
How many rows in this file don't have B? 6. Cool. So we can formulate questions on the fly as we come up with stupid pipelines like this, or we could have a question ahead of time and figure out how to put our little puzzle pieces together to answer it. And this takes a bit of creativity, but you start noticing some things that get done a lot and they kind of start sticking in your mind. Yeah.
So like when you do like LL and then the output that comes out, it's like in columns, but it doesn't look like they're separated by tabs.
They're not.
So can you still do like
Sort on,
yeah, like in the column stuff with those?
you have to first translate any 2 or more spaces into a single one, then cut it on those and then sort.
Okay.
So I've got in lesson 3 this super tiny text here. Copy that. And we're going to paste it into a file. So I'm going to go into my lessons. Lesson 3. Okay. So I'm going to, as it says here, make a new file called seeks.fasta. So I'm going to just say nano seeks.fasta. I'm working in my lesson 3 directory to keep this nice and tidy. I'm going to paste it in. And then save that file. Control O. So this is real data. It's very tiny little subset just so that we can kind of play with it. But this is a very classic type of file for storing genetic DNA reads or protein reads, FASTA. And the way it works is it starts with greater than and then some ID, and this is kind of typical. This ID doesn't necessarily have to mean much to you, but it's the serial number of the sequencing machine. And then all this stuff here is giving you actually a location on the chip from the sequencing machine. So you load your DNA onto the chip, put it into the machine, and it's actually just a really high resolution camera that does your DNA reading. Isn't that weird? It's just a super camera. That's what an Illumina sequencer is. You wash over an A, T, C, or G that's bound to a little fluorescent tag. You wash A over the chip, and it binds to what? What does A bind to? T. If it does, in that little spot on the chip where that DNA molecule was that it wants to read, it'll release that fluorescence and you get one photon. And the camera picks it up in that exact location, and that location is pointing to a certain sequence. That is an address to a location on the chip for this machine. Okay. Weird stuff. And here's the reads that it got. They're kind of long. It's running off the screen here. But it's just on a single line.
So for like fast, like they don't have the full like complete things. They have like fast use for like use and then fast use. They're complete assembled ones.
Nope. FASTA is just a file storage type that is alternating. One line starts with greater than and identifies the sequence. The next line after that is the sequence. Line 3, new sequence header. Line 4, the sequence associated with that. So this is incredibly common. And it can be for complete genome, it can be for a short read. What the important thing is that it was alternating format. People came up with this for reasons back in the day, and we still use it.
And fast use.
I don't think it's good reasons, but get used to it. FastQ just also has quality information better. We'll see one of those next week. FastA is easier to work with because it's alternating. ID sequence with that ID. ID sequence with that ID. So I've saved this file. All right, I've got seeks.fasta now. And let's ask some questions. How many lines are in this file? How do I do that? WC-L. 24. Okay. How many sequences are in this file? You could, but Bash is actually really terrible at math. It's kind of built in. Don't rely on that. Its purpose is for working with text. Let's look at the file again.
Could you do something with like the dash? Like you said, everything with the ID first of like the.
You're onto something there.
So,
You notice this is why they did this. Every ID line starts with greater than. What program searches for patterns? Okay, so I can cat seeks.fasta, pipe it to grep, and then give it the pattern I want to find, which is what? We could do that. Put that in quotes. But that's not exactly the pattern that you described to me. What if greater than was somewhere in one of these sequences? And if you see FASTQ files, that greater than actually is an indicator of sequence quality, so it'll pop up sometimes, but not all the time.
would it be like line break?
Oh, you're on something. Line break, then greater than. So you're saying a line that starts with the greater than symbol.
Did you do the RSV?
I could do minus v, so I could get all the things that don't start with that. But I want to show you a special, this is a regular expression. The caret, shift 6. That means line starts with. Okay. I'm not going to have you memorizing all these magical regular expressions because they are obnoxious. And when you see regex code written out, it's pretty gross. But here's a few handy ones. A dot means match any single character. Greater than, or the caret means beginning of a string of a line. The dollar sign means end of line. So this regex here, caret ABC dollar, what would that match? The entire line, it needs to start with ABC and then end. So the entire line must match that. Okay, AB star. An A followed by 0 or more B's. So it's saying like an A followed by either no or infinite number of B's. AB plus. These get really gross. Okay. And so regex, I think is better kept to learn a few key ones and then just Google the rest. GPT is actually really good at regex. You can give it a pattern and say, I'm looking to match this followed by n of any of these characters and then a space, and then it'll match it. So it's an entire language. Regex. And sadly, there's like a bunch of different flavors of it. There's the Perl version, extended regular expression. This one is worth memorizing. Starts with. Hack the whole file, send that to grep instead of my screen, and I tell grep, look for lines that start with greater than. There they are. Now I want to know how many of them there are. What can I do? Type to WC-L. We've got 12 sequences in that file.
So why do we have like greater than understanding?
Sure.
Yeah, that's fine. If we're looking for. Oh, wait, never mind.
Because here's the whole file. We're just asking it to return the lines that start with greater than. I showed that part. This is how I will often, and it's kind of good practice as you're building up a pipeline, look at the output from each step as you go. Be like, okay, yep, that's looking correct. Now I just need to count the number of those. When DNA is transcribed to RNA, thymine becomes uracil. Okay, convert this to RNA. I do.
Or
Translate. Type that to translate, and I want to translate T into U. Cool. All right. How many sequences have ambiguous bases? When a DNA sequencer can't tell if it's A, T, C, or G, what's it put out for you? N. For most cases, that means that we don't get to use that. We can either truncate the read at that point, or we can throw out the whole thing. I mean, this one. low quality. That's common. All right. I would like you on your own figure out how many sequences have ambiguous spaces. And a word of caution, notice that all the headers have an N. So can't just simply search for N's.
Is there like a reverse Python?
Yes, the dollar sign means end of line. Is that what you mean?
Or just like any line like that doesn't start with it?
Yeah, you would use grep dash lowercase b
Oh, yeah,
and invert the matching.
You said how many ones?
How many sequences have ambiguous spaces? Any ends in them?
And like, I know like when it's on the console, it's actually on one line, right? It's not like multiple lines, because like it's controlled.
Yeah,
Right. Okay.
you can tell if it's one line or not by just double clicking. When you double click a word or a line, it like highlights the whole thing. So like there you go. Got it.
Okay, so
What number did you get?
one.
One. Okay. One is the correct answer. I'm thinking through this problem. I'm thinking, okay, I can't just do a grep for n. So if I cat seeks and then say grep n, I can see it's just a bunch of headers and then this one sequence. Okay. But that's still not the answer. I need the computer to give me the answer. And the only reason I can see this is because we're just looking at 24 sequences, not 24 million. So, okay, that's not going to work. I don't want those headers there. So first, I'm going to get rid of them. I'm going to grep inverse starts with greater than. So that gives me just the sequences. And then I'm going to grep for n. There they are. And then I'm going to word count how many lines. Got one.
Is it okay if you do that all in one go?
We need.
Like, instead of doing it multiple times, just typing it.
Yeah, if you could do that in your head all at once, great. This is a nice, easy problem so that it's expected that you could. I'm just kind of showing you like how my thought process works.
Okay.
And this is how I do it in real life too, because usually I'm not asking such a simple question. How many have this?
Yeah.
I have to kind of build it up. Maybe I'm just like dumber than you.
No,
Which is
I
like
was
honest,
just.
that could be like
No, I was just more asking, make sure I wouldn't let the best.
I've been getting dumber for the last 15 years, so it's believable, but I really do have to kind of think about it in steps. And it helps me if I can kind of see what each new link in my pipeline is giving. When I'm working with millions of lines, I don't want to blast all of those to the screen, and so I always end with like a little head 10. And so I'm just looking at what the output would be the first 10 lines. Okay, yeah, that looks right. Get rid of head 10. Let's do the next thing with a head 10, kind of see what's going on. So yeah, I got one there. There's a little built-in shortcut, if you read the correct documentation, that a little dash C just gives you the count of matches. So there's one. All right, here's one. The count of lines that match. Yeah. What is the last sequence in the file that contains G, CCC, TT, CGG? It's up there on the screen. I can make it bigger.
So you can kind of fill in the, like, the number sequence of the index, or,
No, give me the sequence itself.
oh, sequence.
Yeah, but give me,
Okay.
show me the last sequence. The full DNA read that has that pattern.
And you just know the first one,
Last
or
one.
the last one?
Mhm.
Okay. You want like the items here, or just?
It's just the sequence. I'm gonna cat my seats. I'm gonna grep for G, C, 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 T, 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 G, G. Looks like there's two of them. So I'm gonna say tail. Give me the last one of those.
Oh, I did like tack, nice to do.
Oh, tack and grep. Okay, cool.
That one too.
Yeah. As long as you took the first
The first
one,
one.
yeah. There's no right way to do anything. There's just a bunch of wrong ways. Yeah. But what you're telling me, that sounds right. Tack gives you the same thing. Tack and head one. It's the same as tail one.
So tack goes like line by line too.
It just starts reading any input from the bottom.
You don't have to worry about like reading backwards.
No, it's just line by line. All right. What if I wanted the name of that sequence, or in other words, the like header? These don't always just have gobbledygook here. This can be anything. And so you will commonly encounter FASTA files that have like Mus musculus or Homo sapien or whatever, and like it's a bunch of genome sequences. You're looking for some pattern in there. You're like, which organism has this pattern? So you need actually that header line. So how could I modify what I've done here to actually get the name of the sequence, not the sequence itself?
So you get rid of that.
Well, the second I do grep C, G, C, C, whatever, I've lost the headers. Well, I said this as a little throwaway when we were looking at the help file, but I can ask for the lines before also. So I can say, find the matching lines and one line before them. So give me some context around there. Ah. Okay. Now I pipe that to tail. I actually need to take the last two. And then I can pipe that to head and take the first line of that. There's the name.
What is B do again? Sorry.
Before. Capital B is before. And it wants a number, like how many lines before. Capital A is after, and how many lines after. Okay, so we've got really just 1, 2, 3 little programs here. And we're starting to ask more complex questions. How you put them together is the creativity process here, but they're not that hard, are they? No differential equations to mess with here. This is like, oh, we're starting to see that it's kind of straightforward and simple, but as we start putting these together in different ways, we're starting to build some complex pipelines. Okay. And that's the kind of logic behind Bash. Really simple things that do one thing really well, those programs. And they wanted to leave it so they only do one thing really well, really fast, but can work interchangeably with each other. Where the standard output can always become the standard input for the other program. What that means is that the sky's the limit for how we can put together our little pipeline. Questions so far? This little pipe is our friend. Reading the documentation on something like grep is also your friend, because how else would you know that capital B lets you pick the line before? So there's only like 20 of these little programs we're ever going to deal with in this class, the Bash programs, but knowing them pretty well will give you a lot of freedom and flexibility.
Can you type like I know you're saying that they can work with streams like standard errors and things.
Mhm.
And like if we're going like cat like the breaths right there, you're going to the tail. Like and that that specific type, could you write out like a standard error somewhere else too, or
Yes, you could, and that's the T. And so we could write that to a file using the T command. I've never looked up the help for this. Oh, there it is. The T, copy standard input to each file and also to standard output. All right. I have an example of that. Where was this? Oh, it's down lower. There we go. So you can send your standard out to the next program and to a file.
so it's both outputs. It's not just you can't do it one. Like how we
T, you can tell it send the standard error also if you want. That's like a little flag. I think it's underscore E or like dash E. You don't use this very often. But yeah, it could come in handy if like there's a bug somewhere and you're getting an error and you're like, where is this? Put my error report into a file format. And so I'm typing to T, the program, and its whole job is to take that string, copy it, like multiply it, and send it to a file and to the next standard output. Scroll back up. All right, we've seen variables before, so I don't think I need to go over that again. Do I? Maybe. The variables, the idea of like we can just assign something. Remember, there's no space between the name of the variable and the thing you're assigning. This is pretty common that we wind up with like some sort of base name. This is an accession number from NCBI representing some sequencing rate or some sample. And it's very common that a bioinformatics program that we're going to use it's gonna say like, okay, give me the forward name of your file and the reverse, because remember, Lumina reads things one direction, turns around and reads them again. We get 2 files for every sample. One read in forward, one read in reverse. And so all this software is like, all right, give me the file name and the path to it for your forward read, your reverse, and then tell me what to name the output. And then tell me what to name the log file. Fine, if we're doing that for one sample, it's easy enough to type it out. If we're doing it for 30,000, it's a problem. So we can use our variables and kind of tack things onto them. So I'm going to copy this here. I just made myself a variable. Sample ID is that. I can say echo sample ID. Neat. Echo sample ID underscore forward dot FASTA. Unhappy. I'm coming. What did it do? It gave us what? Dot FASTA? It gave us just that. It looked here and said dollar sample ID underscore forward. Oh, I don't have that variable. So it gave us nothing. And then it gave us dot FASTA. The curly brackets are the safe way of calling a variable. So dollar curly bracket around my variable name says this and this alone is the variable name. Everything else is extra fluff that I want you to look at, but it's not the variable. I will often write when I'm looking through the contents of a variable, I'll just write it like that, even if it's really straightforward. Just trying to teach myself good habits, that this is the nice, safe way, putting your variable and saying this variable name. What it also means is that we can use a variable name and have a bunch of different add-ons for it. So I could say forward equals sample ID underscore forward dot FASTA. And then I could go up here and say reverse equals that. Echo forward and reverse. Using little curly brackets, and I can start building up variable names. I'm showing you the most common use case for this for working with thousands of files is you can use some base name. This sort of thing is going to be going at the top of your scripts in this class. So you're working with a remote computer that has its own file path starting from weird directories that you're not familiar with. They're not the same on your computer. And, you know, if you port this out to somebody else's supercomputer, guess what? They're going to have their own file paths. You don't want them having to change 500 lines of code to reflect all these different file paths. Let's just make it a variable. We say like, hey, here's the directory for this particular little library. So I copy that, paste it in. Great. And if I want to refer to a file, ooh, I spelled it as well. Okay. If I want to refer to a file, echo. What's going to happen here? Where would I use something like this? In the script.
You have a directory, this is the directory you have, and like you can say like if you want to recreate this code, change the working directory.
That's pretty much it. Like, look, I don't know what computer you're gonna be using this on, but I'd have a little message at the top of my script. It's like, this works on my cluster. If you want it to work on yours, change the path to GDAL to wherever it lives on your computer. And then that's the only thing they have to change. Script. Now, that's still kind of annoying. And so what do software devs do instead? Docker, where we just package GDAL with our program and it lives in a known spot. That comes with its own set of problems. You have to have Docker. You have to know how to use Docker. You have to have Docker installed on your HPC. And so it actually creates more problems than it solves a lot of the time if you're just wanting to like answer your biological questions. Here, let's change this path. So you'll see this sort of thing a lot where we're creating directories by or creating variables that have some directory in them. All right, try these two. Given that output, what's the difference between single and double quoting in Bash?
And what the variables are just keep as a string.
Look for variables or keep as a string. Yeah, I like that. The term you'll see like ChatGPT referred to help files is double quoting allows variable expansion. Single quoting interprets as literal. So if you want your variables to expand into their contents using $, you need a double quote. Using single quotes can be very handy though, like if $, is part of your regular expression you're trying to do, you don't want expanding to some variable. Single quoting is the way.
Is there like other users where like single versus like double quote? Is there kind of like I know like when we were doing like the strings from before and like or like another like grep.
Yeah, like grep. Yeah, so exactly the same in grep. Single quotes are literal interpretation. Double quotes allow for expansion. Variables. Let's see. So if I cat my seek stuff faster here and I find some pattern, I'll just copy this right here. 4Gs TCC, sure. Cat that. Type to grep and search for that pattern. Cool, I found it. Right. But what if that pattern was actually stored as a variable somewhere? So my pat equals that. Grep for that's convenient. If I single quote here, found no match. So double quoting allows that variable pat to expand to its actual value and it's search for it. This is also a really handy sort of thing because you can be creating variables on the fly over here and then searching for them.
So is it just best practice to double quote always?
No, because sometimes when you're doing regular expressions, that $, means end of line. You don't want it expanding. So if you're grepping for a pattern and you literally want to look for $pat, you have to single quote. Yeah.
So make the variable confusing to me.
Okay,
So you could use them in theory to search for things faster, or what is like the,
what if I didn't know ahead of time that the pattern I'm looking for is 4G's TCC? But I'm pulling that information from some other calculation. I can have that calculation store the result as a variable. And then I can call that variable later down in my pipeline without having to know what it is ahead of time and type it in manually. Yeah.
okay.
And yeah, we got time for looking at command substitution and process substitution. Okay. We won't have too much time to play with this, but the rest of this should walk you through it at home. And we can talk about it again next class. But sometimes you don't want the text you typed, you want the output of another command. Okay. Let me just show you this in practice. Echo dollar parentheses PWD. So it's dropping it in place, basically saying the dollar parentheses is command substitution. It's saying whatever's inside of the parentheses will be evaluated, and that's what I'm going to give as my standard input. So echo dollar LL, oops, LL pipe head 1. Cut based on a space delimiter field 2 of that. Oops, hates it.
What's the point of this if like you're not even getting like the variable, like a variable name? Like, and
Think of it like an anonymous variable.
Yeah.
Yeah.
But could you just like do something like how if you like wanted to, or I wanted to.
For these simple cases like echo, yeah, you can't. In fact, echo is just sending it to my screen anyway.
Yeah.
And so I could just say LL head N 1. I get it. Let's do it with the raster file. So if I cat my seeks, here it is. Let's see, what can I do? Translate the view. Okay. And then tail 1. There, we get the RNA version of our final sequence. Suddenly, I can wrap this in $, and that becomes some sort of standard input that I can feed into any program. So it lets me take a little pipeline, just a little simple thing that I've got, like, I want this to be the standard input for that program. For a program like Echo, cool, we don't even need to do that. It would send it to the screen anyway. But for a program like stats.sh from the DB tools package, it won't. It's like, give me your standard input. It's like, I could feed it this instead. This becomes pretty powerful when you start chaining things together in longer pipes, working with more than one file. So we can piece together parts of 2 separate files using this command substitution. I don't know that I have enough time to walk you down through the process of this before class is over. So kind of leave it there as a, see if you can figure this one out at home and then come with your question, and we'll start using command substitution and process substitution. This captures the standard output of everything inside and uses it as standard input. This process substitution does something similar but slightly different. It becomes a fake imaginary file. There's plenty of software that doesn't want standard input from your screen or from some other program. It wants a file name. You don't want to give it that file name for you got your reasons, or you're dealing with dozens of file names. You can say, here, whatever happens in this pipeline I write, send that to an imaginary file called dev f64. It's a stupid name for it, and use that as a file. So this makes an imaginary command, imaginary standard input. This makes an imaginary file. So here's a good example. Oops. Just typed it. If I just type in date and hit enter, it gives me the current day and time.
I need to figure out like what, they say like with like PWD, like, is PWD like always gonna be the variable name? Or is data always, A gonna always be the variable name? Or
That dollar sign doesn't mean variable, not in this case.
okay.
The dollar sign parentheses means evaluate this. It doesn't have to have a variable name. It's a command that you're doing.
Okay, so
Yeah.
just, it's this, it's like,
Yeah, so I can say echo the dir I'm currently in is dollar. Please evaluate this. It's just like a little inline drop in, evaluates whatever's inside and becomes that pretty quickly. Word count L update. Hates that. Word count. No such file or directory. Yeah, well, this is the result of date. And it thinks I was saying, give me the lines of a file named the, a file named Seth, file name 11, file name 104836. And so it's like word count's looking for a file. So I can give it a fake file by changing that dollar to this. So I said, here's date, send it to a file, an imaginary file, and then word count's like, yes, I love that file. I will count the lines in it for you. And here's the result. There's one line in the file dev fp63. Okay, well, that's a file. I should be able to cat it. It's an imaginary file. You got two important imaginary files, this one and then dev null, which is the go away forever file.
is like a good way to think about like the dollar sign that seems like running that little program within it and then just going directly into your line.
Yeah, it becomes any standard input that you want.
But so it just like runs in the, you're just assuming that the,
It runs, it starts a separate process is
Yeah.
what's happening actually in the background. So there's a separate process in your computer. It's like, hey, I need a new shell. And it actually does make a new little shell. It evaluates what's in there and drops it into your current shell. And the less than parentheses is it makes a temporary fake file. Yeah. All right. Work through lesson 3. Make sure you're doing the little practice tasks as well. those should be doable at this point for you. Like practice batch number 1 and 2. Those are in resources, practice exercises. Yeah. This one, yeah, Unix 1 and Unix 2. So I've got you all the answers here, so you can see what it should look like. See what it takes of those answers.
Maybe we have the one Tuesday, or is that gonna be?
Thursday.
The quiz is Thursday.
Yeah, I want you to have more time to like do this at home,
Yeah.
do the practice, get to where it's kind of simple. And then expect something like 1 or 2 of these tasks to be your quiz. Yep.
And then for what assignments we need to do. Not Tuesday,
Thursday too on that, yeah. Cause we're starting to learn like a bit more at a time now. I'm just throwing like, here's translate, here's graph, here's set. So let's spend some time waiting in it. I want you real comfy. Because next up, we're gonna actually start learning about how to download and install programs on the HPC. Cool.
I have, I have a question.
Yeah.
I already changed my schedule, but when we were doing, this stuff, and so, and we wanted to kind of just. I tried to translate